Welcome everybody to this extraordinary presentation today. This is under the umbrella of the 25th celebration of WIE 2022. Our speaker is Dawn Tilbury, and she will be representing the Control Systems Society. I will pass the floor to Bozena in a moment, but before doing that, I would like to thank everyone for being with us today. I would like to remind that so if not speaking, everyone should have a video and the microphone off. And please post your questions for the speaker on the chat. The questions answer sessions, it would be at the end of the talk. And I think I will stop there, pass the floor to Bozena. But not before thanking once again Dawn Tilbury, Professor Tilbury, for joining us today, and all the people who have been contributing for the success of this Extraordinary Women, Extraordinary Science seminar series. I will get back again to that at the very end. But at the moment, so Bozena, the floor is yours.
Thank you, Cinzia, and good morning, everyone. And good morning from Lawrence, Kansas. And it's my great pleasure and privilege and honor to introduce my colleague, member of Women in Control, Dawn Tilbury from University of Michigan. And she will say important things about herself that are important to everyone. But I would like only to say a few special things. Dawn is that one I met when she was still a student, and we were forming Women in Control group, which is one of the most successful group that I've been engaged. So, and Dawn is breaking ceilings continuously. I remember I introduced her today, 2022, but I remember 2017 in Toulouse, in France, at the Congress, when Dawn was only second female in the history of over 60 years of IFAC, International Federation of Automatic Control. And at that Congress, she was presenting. I remember 2015 when I introduced her, and she broke also record being female engineering at SIAM organization, which stands for Society for Industrial and Applied Mathematics. So she balances, as you can see, she can join mathematics organization, she can join many organizations, and she's fellow of other than IEEE organizations. So, and also what is the most impressive for me from my point of view, being supported for over 35 years for National Science Foundation. I wouldn't be what I am without National Science Foundation, but Dawn was coordinating over 110 programs at National Science Foundation. So for me, she is like hero of knowledge, what people do, which programs, and to which she knows the future. She will say, I'm pretty sure about already 2030. So what is going on? And this is for me amazing role that she operated annually. Charmaine, you can listen, annually over $1 billion. So this, you can see what kind of skills Dawn presents. And she, of course, is president, the first female president of another organization, A2C, American Automatic Control Council. So I could speak forever, but Dawn is limited with the time. So I hope, and now she's the first chair of Robotics Department. She will say about that. So all the time you can hear the first, and amazing things. She's truly remarkable leader and remarkable researcher and remarkable woman in control. So you are now in control, Dom. So thank you so much for being with us.
Well, thank you, Bożena, and thank you for that very nice introduction. Can everybody see my screen? I hope.
Yeah.
Yes,
Yeah.
thank you.
Great. So it's great to be here today. How can you say no to Bożena? Of course, if she asks you to do something, you want to, help her in any way you can, because she has really been such a driving force for women in control. And by the way, isn't that a great name, Women in Control? I mean, wouldn't you want to be a member of such an organization? Anyways, so I will have a few minutes today and tell you a little bit about my background. And then I'll talk about some of my research on trust and control, where humans are interacting with automated vehicles. And Bożena mentioned the new Robotics Department. This is our new building here on campus at the University of Michigan. And if you have an opportunity, would love to have you come visit sometime. So the outline of my talk is, I'll talk a little bit about my background and how I got here. And then I'll talk some about trust in automated vehicles. Wouldn't be a control systems talk without a couple of feedback loops and some models. And then I'll talk about pedestrians and end with some conclusions and future directions. And please do enter comments or questions in the chat. I will try to end a few minutes early so we have time for Q&A at the end of the presentation. So I started my engineering career at the University of Minnesota. I was an undergraduate in the late 1980s, believe it or not. And I chose electrical engineering because that's what my dad was. It seemed reasonable. And at the time, women were only about 8% of the students in EE. Now, one factor could have been the lack of women's rooms in the EE building. At least the EE building was connected to the mechanical engineering building, so we didn't need to walk outside in the Minnesota winter to use the facilities. Now, that was my early connection to mechanical engineering, perhaps, and I was very active in the Society of Women Engineers as an undergrad and even became co-president my senior year. So when I finished my undergraduate degree at Minnesota, I went to Berkeley, University of California at Berkeley, and I was still involved in women in engineering groups. There was a group of women students. They were called WICSE, for Women in Computer Science and Engineering, and we met for lunch every Friday, which was great because I knew pretty much all the women in the department, and I knew the men who were in my class or in my research group. But from my perspective, half the students I knew were women, and so it felt like a very supportive place. And you'll see that connection to finding groups of women to work with or to be friends with is really quite important, at least in my career. So after I went to finish my PhD in electrical engineering at Berkeley, I came to the University of Michigan as an assistant professor in mechanical engineering. And at Michigan, there was a group of faculty, we called ourselves FEW, Faculty Engineering Women. And at the time, there were only a few of us. And we would meet for lunch regularly and get to know each other and share stories and best practices. Now, we've had a lot of progress in the time. And now in the faculty in engineering at Michigan, we're more than 20% women. So 450 faculty, 20% is 90. I don't know them all anymore, which is kind of sad. I used to know them all, but it's still been great to see that growth in women faculty in engineering. And finally, Bożena mentioned that I was at the National Science Foundation. So when I joined in 2017, I was the assistant director, meaning overseeing the entire engineering directorate. And there were 7 ADs, or assistant directors. Now, 5 of them were men, and 4 of them were named Jim, believe it or not. Anyways, the director was female, so we had still quite a good group. And by the time I left 4 years later, with rotation and turnover, there were 5 women and 2 men in the assistant director group. So I wanted to talk a little bit about robotics. Božena also mentioned that I'm the chair of this brand new robotics department. And so how did we start a robotics department? Well, I'll try to tell you the story. When I came back from sabbatical in summer of 2011, the dean asked me to put together a steering committee and say, what can we do with robotics at the University of Michigan? We had 25 faculty at the time in mechanical, electrical, computer science, aerospace engineering, industrial engineering, naval architecture and marine engineering, and probably a couple others. But we were scattered across all these different departments, but all working on robotics, walking robots, driving robots, swimming robots, flying robots, manufacturing robots, medical robots, etc. So we wrote this report and said, you know, this is what we see as robotics. This is the discipline of robotics. Design, creation, analysis, and use of embodied computational systems that interact with physical and human environments. And we said, we need a graduate program, a master's and PhD degrees. We only need to create 2 new courses to launch this graduate program. One is in math, the other is in robotic system, sort of a boot camp design, build, test. 2 new courses, and we can offer mechanical master's and PhD degrees in robotics. Great. We said we want an institute to bring these faculty together around different research directions. And finally, we said we need shared research space. The students that are working on the flying robots should be able to talk to the students that are working on the driving robots, because they're using the same LiDAR scanners, they're using the same MPC algorithms, they're using the same, you know, sensors and actuators. And so it would be really great if we had this shared space, both indoors and outdoors, for automated vehicles, flying drones, biped walking robots, manufacturing robots. We said, this is what we need. We gave this to the dean and we're like, okay, we wrote a report. Sounds good. Wow, what do you know? In 2014, we launched the graduate program. We stole 5 PhD students that had applied to other departments and brought them in, and those were our first PhD students. In 2017, we launched the Institute. Jesse Grizzle became the director. And in 2016, the Regents approved that beautiful new building you saw on the first page, and it opened in 2020. Right in the middle of the pandemic. Of course, we all moved our stuff over here and then went home. So like, okay, we got everything we asked for. Obviously, we should have asked for a lot more, and I'll come back to that. But you can see with this timeline in 2017, I went to the National Science Foundation, as Božena mentioned. So I started there in the summer of 2017, and then in the fall, we moved the building from Arlington to Alexandria. 10 miles or say 15 kilometers across the DC suburbs. It had been planned for a long time. It was well orchestrated. It was still very disruptive. Then in my second year, we survived the longest ever government shutdown, 5 weeks, where the government, not the whole government, but a slice of the government of which NSF was a part, did not have an appropriation from Congress, so we could not pay our employees. Now, because I was on loan from the University of Michigan, they'd already paid my salary to the University of Michigan. So I was still paid and still expected to work, although there wasn't a lot going on. So at our New Year's party in January of 2020, I assured the engineering staff that nothing could possibly go wrong in my 3rd year. After the move and the shutdown, what could possibly happen? Well, you all remember in March of 2020, we had a global pandemic and everybody was sent home, including me. I had been working in Alexandria at the time, except during the shutdown, and I had the choice to stay in my apartment in the DC area or move back to Michigan to stay with my husband, and it seemed like a no-brainer. So I spent the last part of my time at NSF sitting in my home in Ann Arbor, Michigan. So in my 4th year, we had a presidential transition. So it was very interesting for me to be inside the government and be involved in all the preparations for the transition. What kinds of research are we doing? What briefings do they want? What reports do they need? What kinds of funding can we ramp up in alignment with the presidential initiatives? So it was really exciting to see the president's budget, the first budget request of the new administration presented to Congress. because we had a significant requested increase for the National Science Foundation. So then at the very end, my last day was supposed to be June 18th, 2022, or 2021, excuse me, at the end of my 4-year term. And partway through my going away party on Thursday afternoon, President Biden signed the bill to make Juneteenth a national holiday. So I got a little bit of an extra excitement at the end. But it was a great 4 years, and I'd be happy to answer questions about that at the end. But back to robotics. So June of 2021, I come back to the University of Michigan. And while I was gone, my colleagues had been here cooking up plans for a new robotics department. So they had also written another report to the dean that said, we have this great building. We have these great faculty. We have this institute. We need a department that will also have an undergraduate program, because we want the robotics program to be good for the students. Now, some people have said, and I don't hear too much opposition to this, that the best undergraduate major for robotics is a quadruple major in mechanical, electrical, computer engineering, and mathematics with a minor in psychology. So we're trying to take the best parts of all of those 4 majors and minor into an undergraduate degree program so students can get their undergraduate degree and become roboticists in 4 years. And we're doing this with values of respect, outreach, and integrity. And so we're very excited about this. And again, I'd be happy to talk more about that during the Q&A. But I wanted to talk a little bit about research, because I think that's one of the threads that runs through this seminar series, that it's extraordinary women doing extraordinary science. So I'll talk a little bit here about trust in automated vehicles and how that can be managed and leveraged to improve the performance of the human and automation pair. So let's get started. So trust is very important for human-human interactions, as we know. And I think we've seen during the pandemic that it's harder to build that trust if you don't have the personal connections. And that's another story we can always talk about in the Q&A. But there's also important trust with human-machine interactions, right? If you're going to put your car on cruise control, you trust that it's going to keep the same speed and not exceed the speed limit. Of course, if the speed limit changes, that's another thing. So we see in the future that robots will be not just tools for people to use, but teammates. And so they'll need to consider, how do people trust robots and how do robots trust people? So first, let me say what I mean by trust. So we use the definition, trust is the attitude that an agent will achieve an individual's goals in a situation characterized. Hello? Is there a question? There's an echo. Anyways, we define trust as the attitude that has to be uncertainty and vulnerability. So if you're going to trust something, there has to be some risk associated with that, at least in our definition. So we want to investigate what affects trust, how does trust change over time, and what behaviors reflect trust. How can we know if somebody is trusting something, especially when humans interact with robots? So we're going to talk about autonomous vehicles, or AVs. So we see AVs as basically robots that carry people. So safety and comfort need to be addressed. So AVs, if you've seen all the news and all the hype, they are expected to really improve transportation, but people need to trust them appropriately. And I'll come to that in the next slide, I think. So if people don't trust them inappropriately, they can negatively impact both the driver's safety and the performance. So if you have an autonomous vehicle and you're not using the autonomous features, you're under trusting it. You're not taking advantage of the fact that this vehicle can actually do a lot of the driving for you, freeing you up to do other things like, I don't know, check your email or send a text message or whatever. So you're not using the capability. However, if you overtrust it, and you're trusting it to be capable beyond what it's capable of. Say you put the autonomous driving on in the middle of a snowstorm, or in a rainstorm, or in heavy traffic, and pedestrians coming back and forth. We've seen in the news where there have been accidents where the driver completely overtrusted what the autonomous vehicle was able to do. So we want to maintain the driver's trust at a calibrated level in real time while they're in the driver's seat of an automated vehicle. So this is a control problem, right? Calibration. So I'll tell you about the experiments that we've done and the findings that we have. So we have a simulated driving system. You can see my PhD student there. He's got a steering wheel, and there's gas and brake pedals, and he can see what the car is seeing as it's driving along. And we simulate that this is what the Society of Automotive Engineers considers level 3 automated driving. The car can stay in its lane, it can keep its speed. It has a forward collision alert that's imperfect, and this is where the trust is going to come in. There's an emergency brake, so if it sees an obstacle ahead of it and the driver doesn't change lanes to go around, the emergency brake will kick in and it'll just stop. So we assume that the emergency brake works perfectly, so people are not going to get, hurt, quote unquote, in this simulated driving. But the driver needs to take back control of the car when requested, because the car is not able to change lanes autonomously. And we very thoughtfully put a few obstacles in the path that they're going to have to go through. So we're going to model their trust and estimate it. And so for that, we need differential equations, or we use difference equations. We do this at different time steps. So the forward collision alert has 3 different capabilities. It can have a true alarm. I see an obstacle up ahead, and it warns the driver. You can see at the bottom here, it says stopped vehicle ahead, take control now. There could be a false alarm. It could give an alarm, stopped vehicle ahead, take control now, and the driver looks and there's nothing up ahead, false alarm. There could also be a miss. So there is actually an obstacle, but the forward collision alert misses it. So if the driver's not paying attention and doesn't see it, the emergency braking will kick in and the car will just stop. Whoops. Whoa, what happened? Okay, so we have the driver in the simulation set, and we also give them a non-driving related task. We call it an NDRT, which is a search. You can see this search. It's kind of boring, but you have to find the Q in the field of O's. The Q is kind of over there on the far right in the bottom. And they click on the Q, and then it shows them another field of O's. And they get points for all the Qs they find correctly. Now, they have to find, as these obstacles come up, they have to take control of the car. So stop looking at the Q screen, go around the obstacle, put the automated driving back on. And every time there's an obstacle or a false alarm, they're asked to report how their trust changed. Do they trust the system more, or do they trust the system less? The gold standard for understanding how much humans trust something is surveys. So here we have these surveys before and after each event, which you don't want to do in real life. So that's why we're trying to build a model, but we need the data to build the model. So we try to incentivize the drivers by giving them points for the Qs. And we also, if the emergency brake kicks in, like they missed something, they had to go around, they lose points. So, and they get more money for their time in this experiment if they get higher points. So we want to try to estimate that real-time trust in the automated vehicle. I mentioned that self-reporting does have some limitations, but it's currently the gold standard. And so we want to look at, how can we build an estimator from observing their behaviors as well as a dynamic model of trust. So the inputs to our model are going to be these events. There's a true alarm, a false alarm, or a miss. And we're going to assume that our automated driving system knows if it did it correctly or incorrectly, at least after the fact, right? It might have had a false alarm because it saw a shadow up there and it thought there was a vehicle ahead. And then when it finally gets there, like, oh, no, there's no car. That was just a false alarm. And then what do we monitor? What are the outputs of our dynamic model? So we observe their behavior over this interval between the two events. First of all, we look at the focus. How much of the time are they looking at their non-driving related task screen, finding the cues, and how much of the time are they looking ahead at what the car is seeing? So we can put that as a percentage. We put eye trackers on them so we know what they're looking at. We look at how much are they using the automated driving system. Do they have their hands on the steering wheel? Are they trying to drive, or are they letting the car drive itself? And we also observe their performance on their non-driving related tasks. How good are they at finding the cues? Not just are they focused on it, are they looking there, but are they really good at finding those cues? So those are our 3 observed outputs. And then we build this difference equation model where the trust at time t+1 or k+1 is some function of the trust at time k plus a function of the inputs, which are the alarms. And then the output, the driver's behavior, is some output function C times the trust plus some noise. So U and W are noise. This is, an imperfect model, as you might expect. So we get the output from the drivers about their trust change. And then at the very end of the experiment, we ask them about their overall trust with a very long survey, which is kind of the standard in estimating trust. And we had 4 different types of system reliability. Either they were all true, there were some false alarms, there were some misses, or there was a mix of false alarms and misses. And it's well known in the industry or in the literature. True, if the system works like it's supposed to, and all the alarms are true, their trust continues to increase. But if there are false alarms or misses, their trust will decrease. Perhaps not surprising, but we wanted to know how much. What's that function, that matrix B, on how it's going to define the change in trust. So you can see we have starting to look like a feedback block diagram, but we don't have any feedback yet. We have our automated driving system is giving those true alarms, false alarms, and misses into the driver. The driver output is trust. We observe from the driver and their focus, their use of the system, and their performance. And then we have this estimator that's taking in all those variables and giving us an estimate of trust, or T-hat. Oops. So, and then we build a common filter. Control systems engineers in the Zoom won't be surprised. Of course, we have a Kalman filter. It's a very good way to do estimates. And you can see on the right-hand side, this is one participant in one trial where the true trust, true, quote unquote, self-reported, is that black line, and the estimate is the red dashed line. And then you can see the uncertainty cone of how well we're able to accurately estimate their trust. On the bottom, you can see the true alarms, false alarms, and misses, and if it's a true alarm, trust goes up. If it's a false alarm or a miss, trust goes down, etc. So this is one particular trial. And here's another particular trial. Here, the system tracks the behavior because it expects trust to go up if it was a true alarm. This person reported a much higher trust than their behavior indicated, according to our model of trust. And I think that's always going to be true. Some people are going to say, oh yeah, I trust it a lot. And other people are going to be like, oh my God, no way, I wouldn't trust that at all. So I think this is where the bias comes in from the different self-reporting. And then we have this estimator that, is built on an aggregate model. And some people are higher and some people are lower. Okay, so modeling and estimation, we build a Kalman filter. But we want to calibrate that trust. We don't want people to overtrust or undertrust. So we say trust management is we need to estimate their trust and then calibrate it. And so the idea is to identify when drivers are overtrusting the system or undertrusting the system and try to influence them to correct their trust level. Feedback control, this is what we do. So we identify their trust state by comparing what we observe their trust to be. We're not asking them any surveys right now, right? We're just observing. And then we have the different capabilities of the automated vehicles. And then we influence them with communication. So now we come to the feedback block diagram. We have a trust estimator, same as from the previous slides. And we take that estimate of trust into our calibrator. Now, from the automated vehicle, we have an estimate of their capability. And we assume that we know the AV knows what its capabilities are. And I'll talk a little bit about different environments where it might have higher or lower capabilities. So we take their, again, we observe their behaviors. And in this case, we only have true alarms. We haven't done this experiment with false alarms and trying to calibrate. So here's the experiment we run. We have 3 different types of roads you can see on the left. There's a straight portion. This is like the highway. We assume the AV is highly capable. There's a curvy portion, like in the mountains. The AV has medium level of capability. And then there's some dirt roads where the AV may not be able to see as far. So we have this path that the people go through twice, once in one direction and once in the other direction. And you can see here the distance from the obstacle when the emergency brake kicks in and the warning distance. Now the warning distance depends on the capability. In the straight portion, they can see far ahead. In the curvy portion, of course, they can't see quite as far ahead. And in the dirt portion, we assume the warning distance is much lower. So the AV just doesn't have the same level of capability. And this is our trust state. So we have the 3 capabilities of the AV, high, medium, and low. And then we have 3 levels of trust, high, medium, and low. And you can see on the diagonal, if the person is trusting the AV appropriately, then there's no communication from the automated vehicle. It's just silent. If it's over trusting, then there's a warning. If it's under trusting, it's encouraging. So we're trying to nudge the person to trust more or less, depending on what state they're in. And I think I have a video here that will show how this works. You can
stop vehicle ahead.
So there's the stop vehicle ahead. Their trust is calibrated. It doesn't say anything else. So the AV is silent. I mean, it still gives the warnings about trust, about stopped vehicles ahead. And you can see here he's finding the cues.
Hey, this is an easy road. You don't need to worry about driving. I will take care of it while you focus on finding the cues.
So that's encouraging, easy road.
Hey, this part of the road is not very easy. You can still find the cues. But please pay more attention to the road.
So warning, I need you to pay more attention.
Look, I told you, I do need your attention. I can feel the road is terrible. I don't know if I can keep us totally safe.
So these are the slides in case the video didn't work. So does that work? Does this control action telling the driver, pay more attention or you don't need to pay as much attention, is that effective in changing their trust? And so this plot here shows that the warning message were able to successfully change the driver's trust. You can see in the if they were under trusting and it told them you can trust us more, their trust increased by about 17 points on average. If they're really over trusting it and they got that extreme warning, their trusting behaviors, this is the estimate of their trusting behaviors, decreased by almost 20 points. So we're able to influence, I won't say change, influence the driver's trust, at least their trusting behaviors. This is all based on their observed trusting behaviors using our Kalman filter. You'll also note these are real people. There's a lot of variability. This is not trying to control an electric motor where you can get, very pinpoint accuracy. here's a plot that kind of shows what that looks like, where the trust estimate is shown in the purple line, and the gray boxes are the capability of the AV. So in the early stages, we'd want the driver to trust it more. So we give these encouraging messages, and you can see after the second one, it does jump up a little bit. But then the AV capability changes to be more moderate, and it does manage to keep the trust calibrated. And then after the road switches again and the capability decreases, you want to have the driver basically watch the road more and don't do as much on finding the cues, and it's able to make those shifts. It takes a while. You know, this is between two events, which is, you know, over a minute or 2 minutes. So it's not instantaneous, but I think it is an example of the way we're able to change the driver's trust in real time. Okay, I have a few minutes left, so I'll talk just briefly about pedestrians interacting with automated vehicles. So when you have an automated vehicle, you need to think about, if you're coming up to this intersection and you see a pedestrian, should you keep going? Should you change lanes? Should you stop? Question. The AV is not sure what the pedestrian's going to do, and the pedestrian's not sure what the car's going to do. This communication, you know, if there's a driver there, you can wave at the pedestrian and say, yeah, go ahead. And how does this happen over longer time? As you're coming up to an intersection and you see pedestrians, what's the pedestrian going to do? So we want to be able to have the automated vehicle safely and comfortably navigate around pedestrians. So we're going to focus on urban scenario where there's a mid-block crossing, meaning there's no intersection. And this is where there's no signal. So it's very unclear who has the right of way. I don't know about where you live, but in Ann Arbor, if they have these things, there's usually a big sign that says pedestrian crosswalk. State law must stop for pedestrians in crosswalk. But how do you know if they're going to cross? So the AV has to be able to predict what the pedestrian's going to do and then plan how it's going to get through that intersection safely with the pedestrian, and not just sit there and wait while the pedestrian waits and have this, you know, dance where nothing ever happens and nobody gets through the intersection. And we want to do this in real time. So the pedestrian has really only a handful of things they can do. They approach the crosswalk, they wait, they cross, and they walk away. And so we build this finite state model that basically encompasses those 4 states in a finite state machine. And then within each state, there's a difference equation. Again, we use discrete time, where their position X, which is really X and Y, is continuous velocity or 0 velocity. And it can change direction when they switch from walking along the sidewalk to walking away. And you can see when they're coming to the crosswalk, there's some probability that they're going to wait or they're going to walk away. They could keep walking on the top side of the sidewalk. When they're walking away, they could have been approaching a crosswalk, or they could stay where they are. You can see this little loop. And then if they're waiting, the only thing they can do is cross or wait. We don't model that they wait and then they decide to walk away, although we could probably add that in our model. So we have 4 discrete states and then the continuous pedestrian states of their position and velocity. And this, when they're walking, we use constant velocity, which has been shown to be pretty accurate. And then the transitions between the discrete state are either guard conditions on the position and velocity, or the probability that they make a decision, change their mind. So we build, again, we want to get some data, and we could try to put some cameras up around the intersections around here, but we decided in order to get really good data, we should build our own experiment. So we have this virtual reality omnidirectional treadmill where the person stands on the treadmill and puts the AV goggles on, and now they can walk and turn in any direction on this omnidirectional treadmill. And within the head-mounted display, we have an eye tracker. So we can see this is a view of what the person sees looking through the augmented reality. And so we did 30 participants. And then we have a control So we use that data to build the model, like I showed you, the 4 discrete states. And then the controller is trying to consider safety. We don't want to hit the pedestrian. Performance, we want to get to where we're trying to get to without violating the speed limit. And comfort, we don't want to accelerate or stop too fast. So that's the objectives of the controller that we build into the model predictive controller. And so again, we have this unsignalized mid-block crossing where it's a one-way street, very simplified, and the controller uses acceleration control. So you can see when the car is coming up here and sees the pedestrian, it's going to build a model using that 4 discrete states of what the pedestrian might do and use those potential futures of the pedestrian. The pedestrian could keep walking straight, or they could choose to cross. And if they choose to cross, how can I do my control to make sure that I get through the intersection safely without hitting the pedestrian? And so we build this controller and compare it with a baseline. And we can demonstrate that we have, oh, my slide got a little bit screwed up here. So these little red X's are when in the baseline controller, the AV actually hits the pedestrian a couple times in simulation. With our model predictive controller, it does not, but it has pretty good performance. So that's the end of my formal presentation, and I'd be happy to answer questions about either of those 2 projects. Those 2 PhD students did great work, and I had more time to talk about one than the other. But so what's next? So in conclusion, I guess I just wanted to say, we believe we can estimate the trust in the driver from their observed behaviors. Just watching what they're doing, we can have a reasonable observation of what their trust is. And then we can calibrate that if we think they're over trusting or under trusting. And then we can build a model of pedestrian behavior so that we can predict within some bounds of what the pedestrians are going to do. And I think our key insight was that there's really only 4 discrete states for the pedestrian. They're walking along the sidewalk, they're waiting, or they're crossing, or they're walking away. So they're, not too many different things. And, research shows, and our data from our modeling, which I didn't have time to go into, does show that constant velocity is a pretty reasonable estimation of how pedestrians work. And that if you have those potential futures of the pedestrian, you can react to pedestrian behavior. If you just assume they can walk in any direction at their maximum speed, the AV may never cross because it would never be safe to. So I think things we're working on now is really thinking about more diverse domains beyond driving. We're looking at warehouses, we're looking at manufacturing, we're looking at some automated driving, but more supervised autonomous systems that the ground vehicle is purely autonomous and just being supervised by a person. Also, I think most of the work that's been in the literature is looking at how much does the human trust the autonomy or the automation. But in some cases, should the automation trust the human? I mean, that's the default, that the human driver is the primary responsible person. But as we have seen from most of the accidents are caused by human error. Should we always trust the human? And in what cases shouldn't we? And how would we consider what does it mean for the automation to trust the human? And when should they not? And if they're not trusting them, how should they indicate that? I guess that's the end of my slides. I thought I had one more bullet. But anyways, I'm sure there's lots more directions, and I'm sure there'll be lots of good questions for me on this exciting topic of humans and automated vehicles. I think I'll stop my share. So see, I did end in time, like Božena said I would.
Can you see trust? I trust fully. Anyway, it's absolutely amazing for me. Each time when I introduce Dawn, she speaks each time about something else. But this talk is most inspirational and the future. this is the future. And not only I salute to you, I have to admit, I cite you for the last several articles. I always quote your statement, the science is the strongest when the science comes together. So this is just a gorgeous, beautiful statement. But today I salute you for adding mathematics to that electrical, mechanical, computer, and so on. Because what I've seen here is amazing opportunity for mathematicians, for students in mathematics. You open somehow the door for, because look, you have so much probability. I currently teach probability for engineers, mathematical statistics, and you have those estimations, aggregation, you could do weighted aggregation, you interpret noise as imperfection in system. I interpret that noise shows stability or destabilization in system. Anyway, I salute to you. It's just gorgeous. You need to come to KU to just show students that it makes sense what they learn in mathematics, because it's also, you speak about states, so you have Markov chains and all up opportunities for modeling and so on. Anyway, can you see I could speak forever, being so inspired by your talk today, but I'm sure we already can see questions, and Cynthia, you can handle questions, or everyone who has question can open camera and ask directly a question.
I think I can see one already on the chat from Miguel Vélez Reyes. And this very technical one, is there a concept of observability for the trust to guarantee convergence of an error in the Kalman filter?
Excellent question.
Excellent question. Absolutely. You need, in order for the system, for the Kalman filter to converge, it needs to be observable. But I will say, you know, the model that we've created is very, I'll say, you know, it's not based in any physics, right? We have this model of trust that we have 3 inputs and 3 outputs and 1 variable. So the state variable is just trust. There's 3 inputs and 3 outputs, and how you put those inputs and outputs together to create the trust that interacts in each state. Yes, you need to have the concept of observability, but you know, it's a concept that we believe is appropriate for what we're able to do, because we can't really change the trust of the person, but we can change their observed trusting behaviors, which are these 3 outputs that we monitor. So yeah, I think the concept of observability and controllability are interesting when you think about humans. And, you know, having been in the control field for a long time, I mean, people don't like to feel like they're being controlled. So we try not to say that we're trying to control their trust, but we're trying to calibrate their trust and manage their trust. And so we're using a lot of different words than control. But yeah, observability. And I think as we move forwards with the AVs in industry, what is reasonable to observe? I mean, a lot of the the systems, I won't say AVs, with automated driving assist systems, right? Like lane keeping, speed control. They're looking at you. They have cameras in the vehicle, and they're watching what you're doing, and they're watching whether you're watching the road up ahead, or your cell phone, or you're playing with the radio dials or whatever. They are absolutely watching that. That is something that is reasonable to observe. Now, we control this non-driving related task that look for the cues. That's not reasonable in the real world, right? If someone's reading their email or watching a movie, you have no idea how well they're performing on that. You just know that they're not looking at the road. So trying to think about what are the minimal things you can observe will be interesting to think about. What does it mean for observability? What can you actually monitor?
But I like very much the translation, what you presented, and translation into control system language is nice. It's another way of just view that. I like that. So anyway, other questions, Cynthia?
But I don't see others on the chat, and I probably will take this opportunity to ask a question that really came up while you were talking. So in the Robotic Institute that you mentioned has been formed, you said that there will also be psychology, either majors or minors. And there is a lot of psychology in this, let's call it control. How do you read, where do you see the psychology playing as a science within the organization and the programming, actually? So how do you think that this could really fit together, considering that it is less precise?
Right. Well, I think we're bringing it in mostly through human-robot interaction. So in our undergraduate program, we have a required second-year course on human-robot systems, where students will need to work on and define what robots can do, how they work with humans, what the humans can do. And I think that will have some elements of psychology in it. It's currently taught by a professor who's from industrial engineering and ergonomics, and a professor from the School of Information who's trained in social science. So some elements of psychology, but I think that human-robot systems and human-robot interaction definitely has concepts coming from psychology. Like the literature in trust is a lot coming from psychology. The work that was done in collaboration with my colleague from the School of Information, whose background is in social science. And so he's the one who brings the trust. I bring the control and the feedback and the estimation and monitoring. And so it's a great convergence collaboration.
It sounds fascinating, not easy, but I'm also thinking about the pedestrians, for example. This is more sociology. So I think probably one can probably determine and predict the reaction of a pedestrian when the pedestrian is facing certain situations. I am sure that there are probably probabilities that there would be different type of reactions. And so
right.
It's so fascinating.
I didn't talk about the results here, but in that same driving simulator or the walking simulator with the pedestrians, we put them through trying to cross that road with AVs coming up. We put them in the simulator. There were like regular cars that looked like they had a person in the front, and automated vehicles that had no driver and one of those laser scanners on top. And their crossing behavior was very similar in the simulator for both types of cars. And if you compare it to the sociological literature that looks at what gap do people need before they cross the street in front of a car, it's very similar. What we found in our virtual reality simulator and what's been observed in the wild. So I think, yes, you want to relate back to those literatures where people are coming and understanding how pedestrians behave, but we can get much more accurate and lots more data. Yeah. In a controlled environment, we know exactly where the car is and how far away it is and things like that. So I think that's the advantage of using a simulator.
Sorry. No, just to complete, Bozena, sure. Because something came to my mind, and it is the fact that electric cars at the end had to resort in creating the sound of the engine. And this because it was so disconcerting. And you just mentioned right now, maybe you could really have, if the vehicle is completely unmanned, that there could really be someone who is not really a person, but it is really sitting in the right place, and see if there is a different reactions. And sorry, Bozena, I didn't really mean to be rude.
No, very good. I wanted only to say that I never say that, but during undergraduate, I also study psychology. The reason why I study psychology, because I believe in intuition, in good intuition. So when I teach that probability, I observe that intuition that came also from psychology helps tremendously to have some feelings, some, directions, so what to do and what to make and so on. So psychology plays a very important role in all this setting, and I trust that's why I salute not only for adding mathematics, but mathematics was added equally equally to others, but psychology, she mentioned minor in psychology, and I fully agree. It helps, it will help that common sense, for common sense, that intuition and common sense, what I teach in statistics, common sense, use that in estimations, what she mentioned so much. It's absolutely, yeah. Other question, we have probably for one more question or two more questions, and you can open camera and ask question directly to Dawn. This is such an opportunity. You see, I always believe that after listening and being so inspired, you have that delay. You just simply think about that, and then it comes so many questions. So Dawn has to come back, and I will find a way how to bring her back after thinking, because I can see also students here. So anyway, it's great. Any other question?
I think, Božena, we probably will need to close because we know that Dawn has another commitment in 1 minute. So I would like to, well, thanks Dawn very much for this inspiring talk. I would like to thank you, Božena, for being such inspiring to all of us and all the people attending today. And it's a great thanks also to all the WIE support office for their continued support, for Ramalata Marimutu and her team for the publicity, and I'm looking forward to seeing you all again for our next extraordinary talk. Please know that Dawn's presentation will be available on the website, and I've been putting the link on the chat together with all the other celebrations and all the other extraordinary presentations. Dawn, we'll let you go. Thank you so much for being with us today and for this fantastic presentation. I'm sure there will be a lot of inspiration for all the students and non-students today.
Thank you very much. Have a good day, everyone.
You have nice thanks in chat, Dawn, and thank you, Sharman, for being with us as our angel. So thank you very much, Cynthia, and thank you, everyone. Thank you.